It is indeed possible for harmonic currents to exist on the secondary side of a transformer while remaining undetected on the primary side. This discrepancy can arise from various factors, primarily the transformer's sizing relative to the load and the nature of the load itself, specifically whether it's linear or nonlinear. A nonlinear load draws current in a non-sinusoidal waveform, injecting harmonics into the system. The magnitude of harmonics on the secondary side, when compared to the primary, hinges on the load's specific characteristics. In certain scenarios, these secondary side harmonics can reach levels as high as 50% of the fundamental frequency current. These elevated harmonics on the secondary side introduce several potential issues. Firstly, overheating of the transformer becomes a significant concern. Secondly, the transformer's efficiency can be notably reduced. Thirdly, increased voltage distortion appears on the secondary side. Fourthly, there is increased current distortion on the secondary side. In scenarios where a customer experiences transformer overheating, even when the utility reports no primary side issues, the underlying cause could very well be harmonic distortion. This discrepancy might stem from an inadequately sized transformer or the presence of nonlinear loads within the customer's facility. To accurately assess whether harmonic distortion is indeed the root cause of transformer overheating, it is crucial to measure harmonic currents on both the primary and secondary sides of the transformer. A significant disparity between the harmonic currents on the secondary side and those on the primary side strongly suggests that harmonic distortion is contributing to the overheating problem. Nonlinear loads are a significant source of harmonic currents in electrical power systems. These loads draw current in a non-sinusoidal manner, injecting harmonic currents back into the power system. Common examples of nonlinear loads include variable frequency drives or variable speed drives, electronic ballasts, computers, and other electronic devices. The presence of harmonic currents can lead to a variety of problems, including transformer overheating, increased losses in electrical equipment, and interference with communication systems. To mitigate the effects of harmonic currents, various techniques can be employed, such as using harmonic filters, installing properly sized transformers, and implementing power factor correction. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies, while properly sized transformers are less susceptible to overheating caused by harmonic current. Power factor correction can also help to reduce harmonic currents by improving the overall power factor of the electrical system. When evaluating a transformer's suitability for a particular load, it's essential to consider not only the apparent power requirements, which are expressed in kilovolt amperes, but also the potential for harmonic currents. Standard transformers are designed to operate with sinusoidal currents at the fundamental frequency, typically 50 Hz or 60 Hz. However, when nonlinear loads are present, the transformer must be capable of handling the additional stress caused by harmonic currents. This additional stress manifests as increased core losses, winding losses, and dielectric stress. To address these challenges, K-rated transformers are specifically designed to withstand the effects of harmonic currents. The K-factor represents the transformer's ability to handle harmonic currents without exceeding its temperature limits. A higher K-factor indicates a greater capacity to handle harmonic currents. For example, a K4 rated transformer can handle more harmonic current than a K1 rated transformer. Selecting the appropriate K-rated transformer for a particular application requires careful consideration of the harmonic content of the load current. This can be determined through harmonic analysis, which involves measuring the amplitude and frequency of the harmonic currents present in the load. The harmonic analysis data is then used to calculate the total harmonic distortion, or THD, of the current. The THD value provides an indication of the overall level of harmonic distortion in the system. Based on the THD value, an appropriate K-factor can be selected for the transformer. In addition to K-rated transformers, other measures can be taken to mitigate the effects of harmonic currents. These include using harmonic filters, which are designed to reduce the amplitude of specific harmonic frequencies. Harmonic filters can be installed at the load, at the transformer, or at the main service entrance. Another approach is to use active harmonic filters, which inject current into the system that is equal in magnitude but opposite in phase to the harmonic currents. This effectively cancels out the harmonic currents, reducing the overall level of harmonic distortion in the system. Furthermore, it's crucial to ensure that the electrical system is properly grounded. Proper grounding provides a lower impedance path for harmonic currents to flow back to the source, reducing the voltage distortion and minimizing the risk of equipment damage. Regular monitoring of harmonic currents is also essential for identifying potential problems and ensuring that mitigation measures are effective. Harmonic analyzers can be used to measure the amplitude and frequency of harmonic currents in real time. This data can be used to track changes in harmonic levels and to identify the sources of harmonic distortion. By taking a proactive approach to harmonic management, it is possible to minimize the negative effects of harmonic currents and ensure the reliable operation of electrical equipment. In summary, harmonic currents on the secondary side of a transformer can indeed be higher than those on the primary side, particularly when nonlinear loads are present. These harmonic currents can lead to various problems, including transformer overheating, reduced efficiency, and increased voltage and current distortion. To address these issues, it is crucial to measure harmonic currents on both the primary and secondary sides of the transformer, select appropriately sized NK-rated transformers, implement harmonic filters, ensure proper grounding, and regularly monitor harmonic levels. By taking these steps, it is possible to mitigate the negative effects of harmonic currents and ensure the reliable operation of electrical power systems. The percentage of harmonics on the primary side of a transformer caused by loads on the secondary side can vary significantly depending on several factors. Firstly, the type and magnitude of the nonlinear loads connected to the secondary side greatly influence the harmonic content. Secondly, the impedance of the transformer and the upstream power system plays a crucial role in determining how much harmonic current flows into the primary side. Thirdly, any harmonic mitigation equipment installed, such as filters or reactors, can reduce the harmonic levels seen on the primary side. While providing an exact percentage without specific details is difficult, a ballpark figure can be estimated. In a typical scenario with moderate nonlinear loads, such as variable frequency drives and electronic power supplies, the total harmonic distortion or THD on the primary side might range from 3% to 10%. This means that the root mean square or RMS value of all the harmonic currents combined is between 3% and 10% of the fundamental frequency current. However, in cases with significant nonlinear loads or inadequate harmonic mitigation, the THD on the primary side could exceed 20%. It is important to note that these are just estimates, and the actual harmonic levels can vary considerably. To accurately determine the percentage of harmonics on the primary side, a harmonic study should be conducted. This involves measuring the harmonic currents and voltages at various points in the electrical system and analyzing the data to identify the sources and magnitudes of the harmonics. The harmonic study can also help to determine the effectiveness of any harmonic mitigation equipment. If the utility is claiming that there are no harmonic problems on the primary side, it is possible that their monitoring equipment is not sensitive enough to detect the harmonics. Alternatively, they may be using averaging techniques that mask the presence of short-duration harmonic events. It is also possible that the utility's monitoring equipment is located too far upstream from the customer's facility to accurately measure the harmonic levels caused by the customer's loads. In conclusion, while a ballpark figure for the percentage of harmonics on the primary side of a transformer caused by loads on the secondary side is between 3% and 10%, the actual harmonic levels can vary significantly. A harmonic study is recommended to accurately determine the harmonic levels and identify any potential problems. It is also important to ensure that the utility's monitoring equipment is adequate to detect the harmonics and that the monitoring location is representative of the harmonic levels caused by the customer's loads. The flow of harmonic currents through a transformer is influenced by the transformer's impedance and its winding configuration. Transformers with lower impedance will generally allow more harmonic current to flow through them. The winding configuration, such as delta or Y, also affects the flow of harmonic currents. For example, delta-connected windings can trap certain tripling harmonics, preventing them from flowing into the primary side. Tripling harmonics are odd multiples of the third harmonic, such as the third, ninth, and 15th harmonics. These harmonics are particularly problematic because they can cause overheating in neutral conductors and equipment. In Y-connected systems, tripling harmonics can flow in the neutral conductor, leading to increased neutral current and potential voltage distortion. To mitigate the effects of tripling harmonics, it is common to use a delta-connected winding on one side of the transformer. This allows the tripling harmonics to circulate within the delta winding, preventing them from flowing into the rest of the system. Another factor that affects the flow of harmonic currents is the presence of any grounding impedance in the system. Grounding impedance can limit the flow of ground currents, including harmonic currents. However, excessive grounding impedance can also lead to increased voltage distortion. Therefore, it is important to carefully select the grounding impedance to balance the need for ground fault protection with the need to minimize voltage distortion. In addition to the transformer's impedance and winding configuration, the characteristics of the loads connected to the secondary side also play a significant role in determining the harmonic content on the primary side. Nonlinear loads, such as variable frequency drives and electronic power supplies, generate harmonic currents that can flow back into the power system. The magnitude and frequency of these harmonic currents depend on the specific characteristics of the nonlinear loads. To accurately assess the impact of nonlinear loads on the primary side harmonic levels, it is necessary to perform a harmonic analysis. This involves measuring the harmonic currents and voltages at various points in the electrical system and analyzing the data to determine the sources and magnitudes of the harmonics. The harmonic analysis can also help to identify any potential resonance conditions, which can amplify harmonic currents and voltages. Resonance occurs when the inductive reactance of the system equals the capacitive reactance, creating a low impedance path for harmonic currents to flow. To avoid resonance conditions, it is important to carefully design the electrical system and to consider the potential for harmonic amplification when selecting equipment. In summary, the percentage of harmonics on the primary side of a transformer caused by loads on the secondary side depends on several factors, including the transformer's impedance, winding configuration, the characteristics of the nonlinear loads, and the presence of any grounding impedance. A harmonic analysis is recommended to accurately determine harmonic levels and identify any potential problems. It is also important to carefully design the electrical system to avoid resonance conditions and to mitigate the effects of harmonic currents. Regarding the utilities' claim that there are no harmonic problems on the primary side, it is possible that their monitoring equipment is not adequate to detect the harmonics or that the monitoring location is not representative of the harmonic levels caused by the customer's loads. It is also possible that the utility is using averaging techniques that mask the presence of short-duration harmonic events. To resolve this discrepancy, it is recommended to conduct an independent harmonic study using calibrated monitoring equipment and to ensure that the monitoring location is representative of the harmonic levels caused by the customer's loads. The study should also include a detailed analysis of the harmonic data to identify the sources and magnitudes of the harmonics. If the study reveals that there are significant harmonic levels on the primary side, the customer should work with the utility to develop a plan to mitigate the harmonics. This may involve installing harmonic filters, replacing nonlinear loads with linear loads, or upgrading the transformer. In addition to the technical aspects of harmonic mitigation, it is also important to consider the economic aspects. Harmonic mitigation equipment can be expensive, and it is important to weigh the costs and benefits of different mitigation options. The customer should also consider the potential cost savings from reduced energy consumption and improved equipment reliability. By taking a comprehensive approach to harmonic management, it is possible to minimize the negative effects of harmonic currents and ensure the reliable operation of electrical power systems. To elaborate on harmonic mitigation techniques, several options are available, each with its own advantages and disadvantages. Firstly, harmonic filters are a common solution for reducing harmonic currents. These filters are typically composed of inductors and capacitors tuned to specific harmonic frequencies. They provide a low impedance path for harmonic currents, diverting them away from the power system. Harmonic filters can be passive or active. Passive filters are relatively inexpensive and easy to install, but they can be less effective at mitigating harmonics over a wide range of frequencies. Active filters, on the other hand, use electronic components to actively inject current into the system that is equal in magnitude but opposite in phase to the harmonic current. This effectively cancels out the harmonic currents, reducing the overall level of harmonic distortion. Active filters are more expensive than passive filters, but they are more effective at mitigating harmonics over a wide range of frequencies and can also compensate for changes in the harmonic content of the load current. Secondly, another approach to harmonic mitigation is to use phase-shifting transformers. These transformers use multiple sets of windings to create phase shifts that cancel out certain harmonic frequencies. For example, a delta Y transformer can be used to cancel out tripling harmonics. Phase-shifting transformers are typically used in large industrial facilities where there are significant harmonic loads. Thirdly, reactors can be used to limit the flow of harmonic currents. Reactors are inductors that are placed in series with the load. They increase the impedance of the circuit, reducing the amount of harmonic current that can flow. Reactors are typically used to protect sensitive equipment from harmonic currents. Fourthly, in addition to these hardware solutions, there are also several software-based solutions for harmonic mitigation. These solutions use algorithms to analyze the harmonic content of the load current and to adjust the operation of the equipment to minimize the generation of harmonics. For example, some variable frequency drives have built-in harmonic mitigation features that can be used to reduce the harmonic currents generated by the drive. Fifthly, it is also important to consider the design of the electrical system when mitigating harmonics. For example, using shielded cables can reduce the amount of harmonic current that is radiated into the environment. Proper grounding can also help to reduce the effects of harmonic currents. Sixthly, the selection of appropriate equipment is crucial for harmonic mitigation. For example, using K-rated transformers can reduce the risk of transformer overheating due to harmonic currents. K-rated transformers are designed to withstand the effects of harmonic currents without exceeding their temperature limits. In addition to these specific mitigation techniques, it is also important to implement a comprehensive harmonic management program. This program should include regular monitoring of harmonic levels, periodic harmonic analysis, and a plan for mitigating any harmonic problems that are identified. The harmonic management program should also include training for employees on the causes and effects of harmonics. In conclusion, harmonic mitigation is a complex issue that requires a multifaceted approach. By using a combination of hardware and software solutions, along with proper system design and a comprehensive harmonic management program, it is possible to minimize the negative effects of harmonic currents and ensure the reliable operation of electrical power systems. When addressing a customer's concern about transformer overheating potentially caused by harmonics, a systematic approach is essential. Firstly, conduct a thorough visual inspection of the transformer, looking for signs of overheating, such as discoloration, bulging, or oil leaks. Check the transformer's nameplate to verify its rating and ensure that it is properly sized for the load. Secondly, measure the transformer's temperature using a thermal imager or a contact thermometer. Compare the measured temperature to the transformer's rated temperature rise. If the temperature exceeds the rated temperature rise, it indicates that the transformer is overheating. Thirdly, measure the voltage and current on both the primary and secondary sides of the transformer. Verify that the voltage is within the acceptable range and that the current is not exceeding the transformer's rated current. Fourthly, perform a harmonic analysis of the voltage and current on both the primary and secondary sides of the transformer. This will help to identify the presence of harmonic currents and voltages and to determine their magnitudes. Use a harmonic analyzer to measure the total harmonic distortion (THD) of the voltage and current. If the THD is high, it indicates that there are significant harmonic currents and voltages present. Fifthly, analyze the harmonic spectrum to identify the dominant harmonic frequencies. This will help to determine the sources of the harmonics. Common sources of harmonics include variable frequency drives, electronic power supplies, and arc furnaces. Sixthly, investigate the loads connected to the secondary side of the transformer to identify any potential sources of harmonics. Check the nameplate ratings of the loads to determine their harmonic current emissions. Seventhly, if harmonic currents are identified as a contributing factor to the transformer overheating, implement appropriate harmonic mitigation measures. This may involve installing harmonic filters, replacing nonlinear loads with linear loads, or upgrading the transformer. Eighthly, after implementing harmonic mitigation measures, monitor the transformer's temperature and harmonic levels to verify that the mitigation measures are effective. Continue to monitor the transformer on a regular basis to ensure that the harmonic levels remain within acceptable limits. Ninthly, document all findings, measurements, and mitigation measures. This will help to track the progress of the investigation and to provide a record of the actions taken. Tenthly, communicate the findings and recommendations to the customer in a clear and concise manner. Explain the causes of the transformer overheating and the steps that have been taken to mitigate the problem. In addition to these steps, it is also important to consider the transformer's loading profile. If the transformer is consistently overloaded, it can lead to overheating even in the absence of harmonic currents. Check the transformer's load factor, which is the ratio of the average load to the peak load. If the load factor is high, it indicates that the transformer is heavily loaded. If the transformer is overloaded, it may be necessary to reduce the load or to upgrade the transformer to a larger size. In summary, addressing a customer's concern about transformer overheating requires a systematic approach that includes visual inspection, temperature measurement, voltage and current measurement, harmonic analysis, load investigation, harmonic mitigation, and ongoing monitoring. By following these steps, it is possible to identify the causes of the transformer overheating and to implement effective mitigation measures. The NEC, or National Electrical Code, provides guidance on the installation and maintenance of electrical equipment, including transformers. NEC Section 450 covers transformers, and it includes requirements for overcurrent protection, grounding, and ventilation. NEC Section 450.3 provides requirements for overcurrent protection of transformers. The overcurrent protection device must be sized to protect the transformer from overload and short-circuit conditions. NEC Section 450.4 provides requirements for grounding of transformers. The transformer must be grounded to provide a low impedance path for fault currents. NEC Section 450.9 provides requirements for ventilation of transformers. The transformer must be adequately ventilated to prevent overheating. In addition to these general requirements, the NEC also includes specific requirements for transformers used in certain applications, such as transformers used in hazardous locations. It is important to consult the NEC for specific requirements related to transformers. The IEE, or Institute of Electrical and Electronics Engineers, also provides standards and guidelines for transformers. IEE Standard C57.12.0 covers general requirements for liquid-filled transformers. IEE Standard C57.12.90 covers test procedures for liquid-filled transformers. IEE Standard C57.96 covers guide for loading mineral oil immersed transformers. These standards provide guidance on the design, testing, and operation of transformers. It is important to consult these standards when working with transformers. In addition to the NEC and IEE standards, there are also various other industry standards and guidelines that may be applicable to transformers. These standards may cover specific aspects of transformer design, installation, or maintenance. It is important to be aware of these standards and to consult them when necessary. When working with transformers, it is important to follow all applicable safety precautions. Transformers can be dangerous, and it is important to take steps to protect yourself from electrical shock, burns, and other hazards. Always to energize the transformer before working on it. Use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. Follow all lockout-tagout procedures to prevent accidental energization of the transformer. Be aware of the potential for arc flash hazards. Arc flash is a dangerous electrical explosion that can occur when working on energized equipment. Use appropriate arc flash protection, such as arc-rated clothing and face shields. Never work alone on transformers. Always have another person present to provide assistance in case of an emergency. By following these safety precautions, it is possible to minimize the risks associated with working with transformers.